Creating 5G test scenarios the constraint-random way. The constraint-random way verification CRV at the system level is often considered difficult due to the size of the solution space, due to the number of parameters and their interdependencies dictated by the requirement. So the overwhelming complexity lies not only in understanding the system level requirement, but also in creating a valid constraint, generating a valid scenario via a constraint resolver. In this paper, we present a multi-stage methodology to generate a practical constraint that can be easily solved. Our methodology has been applied to a 5G NR 5th generation U radio communication linked by effectively mapping the 5G NR specification to the SystemVerilog constraint and delivering a constraint-random CR generated test scenarios for effective verification of any uplink downlink system. The constraint-random engine focuses on creating a 5G NR resource grid. So the resource grid is represented of a time and frequency domain, and the CR infrastructure maps and the resource allocation flag requirements are presented in a 5G NR specification into SystemVerilog constraint and builds a slow map with the desired channel types. The key constraint in this paper address is to identify the intersection region for all requirement, the channel type, abstracted parameters along with the interdependence between channels. The solution focuses on breaking down the randomization load effectively to make randomization in this grand scale is a possibility. In the end, we successfully demonstrated a practical 5G NR system level CR SRS generation framework customized for scenario approximately 1% of the verification executed time overhead. So, next one is introduction. The constraint-random verification (CRV) is widely used for block level verification and is considered the industry standard due to its verification efficiency, increasing coverage while reducing the verification time and effort. However, the writing good constraint is involved the task is that requires a deep understanding of the underlying solver. The complexity often limited the use of the CRV to block or the model level. In this paper, we provide a methodology that enables system-level CRV of a 5G NR communication system and breaking down the constraint for over 400 interdependent random variables into multiple hierarchies, so while maintaining a common constraint that applies to all levels. In addition, focus of CRV was shifted to a constraint-random system-level test scenarios generation from a traditional constraint-random stimulus generation with a stimulus generated via a reference model. To achieve this, the effort has been channelized into structuring a randomization infrastructure and putting the use of the power randomization engines provided by the tools that support SystemVerilog. The remainder of the paper is as follows. Section 2 gives a brief overview of the 3GPP, third generation partnership product, and 5G NR specification. Section 3 and 4 describe the challenge of the CRV applied to 5G NR communication system and our proposed solution. So the section 5 outlines the leisure to achieve by the proposed solution, while section 6 concludes this paper. The next one is section 2, a brief introduction to the 5G specification. Like its predecessor, 5G network at the physical layer have a channel mapping divided into 3 broad sections as shown in figure 1. The communication channels are divided into synchronization channels, control channel, and data channel in both the uplink and downlink directions. The 5G NR physical channels of both uplink and downlink for the multiple users are mapped to all the specific resource element arrays and the frequent time and the domain presented on a resource element grid, figure 2. Each of the channel types of resource allocation depends on the various sections of the 5G NR specification, represented by the different parameters, function, and tables. So each of the channel type has different functionality as part of the medium between the NG node B 5G base station and the usual equipment UE, such as a smartphone. The uplink and downlink channel types between the G and B and node B and multiple U is at the same time spaces is the frequency time domain. So now the primary synchronization signals PSS and the secondary synchronization signals SSS are the two downlink synchronization signals used for downlink frames. In order to broadcast the master information block MIB and a physical broadcast channel PBCH is used. The channel state information reference signal CSI-RS is a reference signal RS that is used in the downlink direction for the channel sending. The channel sounding refer to a measurement and estimation of the channeling characteristics such as the power delay control profile and the path loss and the path delay and power angular spectrum correlation matrix. The Doppler spectrum and etc. It's used to measure the characteristics of a ratio channel and so that the correct modulation and code rate and beam shaping and etc. can be employed. Physical downlink control channel PDCCH and the physical downlink shared channel PDSSCH are used to provide control data respectively. So now the figure 1 is a 5G NR channel mapping and core test of the HPPs. So next one is figure 2 is a 5G NR uplink RE grid. A is the empty RE grid for 2 slots and B is RE grid with multiple channels and U is allocated. So the uplink frames are synchronized based on the downlink signals. So physical uplink control channel PUCCH is the control channel transmitted by an uplink, which contains information including channel quality, information and acknowledgement and scheduling request. Physical uplink shared channel PUSCH is used by the uplink user for transmit data to the data base station. So physical random access channel PRACH is used by the uplink user to initiate contact with the base station. The base station broadcasts some basic cell information, including the where the random access request can be transmitted. A UA then is make a PUCCH PRACH transmission asking for PUSCH allocations. The basic station uses the physical downlink control channel PDCCH and to provide the downlink control information DCI downlink control information that indicate where the UE should transmit the PUSCH. So configuring an end-to-end 5G link is accomplished by the setting of multiple parameters from the system level and user level and channel level, and both static and dynamic. So first, the capability of the G node B and each UE need to be set. And these include the system level static configurations such as the number of antennas, radio frequencies, sub-carrier spacing, and maximum bandwidth support. The maximum number of the users can be supported and etc. So based on these capabilities, higher layer radio source control RRC parameters and a port communicated from the G node B to each UA. Once the link is established, the corresponding RE grid is created as specified in round 5 in the snippet in the figure 2, which is a representative of the resources available to be used to communication. The RRC parameters specify the bulk of the configuration each channel can take, and so including partial slot frequency, time, or location of resources. The RRC parameters are considered static as they are only updated by configuration update messages, finally through the DCI. Dynamic parameters are communications to the UE, which provide the post-slot configuration information, such as the uplink grant and the corresponding frequency, time, and domain allocation of the PUSCH. So each uplink grant is given by scheduling DCI and its own PUSCH configuration parameters, allowing these parameters to differ for every PUSCH. So in an example, we show how PUSCH allocation as specified in 6 is determined. Time and frequency are independently allocated and combined into form a rectangular allocation. The time domain as a allocation is determined by a via starting length indication value like this start length indication value as shown in the 1, and where the L is greater than 0 and less equal to less than 14 minus S, as S is star symbol index and L is the number of consecutive symbols. SLIV is determined by a two-step process involving the RRC, and DDI. So the first via RRC and PUSCH resource allocation table is configured. Each row of this table contains the SLIV value and which mapping type A or B to use. Then the via DCI, a row index to be used in communicated for each uplink grant. So to accomplish the matters, to complicate the matters based on a mapping type, there are further constraints on which time domain allocation are valid. Two types of the frequency domain allocation exist, type 0 and type 1, and so a complex method beyond the scope of this paper is employed in determining which type to use, which depends on the RRC and is scheduling the DCI. Once the type is determined, the DCI provides either the RBG bitmap, and in case of the type 0, or the resource indicated value RIV. In case of the type 1, so the for type 0 allocation, RBG bitmap indicated which RBG are allocated for PUSCH, with the number of size of the RGB determined via RRC parameters as shown in the table 1 and the equation 2, and with expression 2, and bandwidth part BWP size and configuration 0 or 1 given as RRC as parameters. So where the RRC is resource block group, where the RGB is resource block group, the nRGB is the total number of the RGBs available within a bandwidth part I of the size, and size BWP is I is and the n start BWP I is the starting resource block number for the allocation. For type 1 allocation similar to SLIV, RIV provides the start RB and the length of the frequency allocation, gain where the financial allocation is determined by the combining RRC and DCI parameters and shown in the expression 3. So this expression is the n side PWP minus RB start is greater than the RBS and greater than equal to greater than so on. As the RB start is the start RB index is LRB is the number of consecutive RBs. So the problems of statement and analysis. Verification at 5G and NR physical system levels is challenging, as can be seen the best possible scenarios covering the RE grid and underline the number of permutations and combinations, evidenced by the simple PUSCH allocations example given in section 2. To separate the valid 3GBP, 5G NR compliant scenarios, new combining different channel types from the multiple users, first we must ensure the all user and channels are allocated within the R8 grid randomly without any overlap. So taking all the parameters across the all users and the channel types, the randomizing according to the constraints in the specification. Then the final allocation of the R8 grid is extremely large, loading onto the randomizing engine and a seamlessly impossible task. As an example, inserting adjusted to channel types of the PUCCH and the PUSCH into RE grid for a single user involves around 500 randomized parameters with more users and channel types sharing a single RE grid. The complexity of solving the constant increases exponentially. So our approach to solve this problem is to come up with an elaborated functional verification list which will have a complete set of the features that need to be verified to create directed test scenarios to achieve the functional verification list. This would involve identifying all combination of channels and users can be allocated in a single RE grid, so to provide all the parameters that will create a valid test scenario to cover directed test. The problem with this is that it is time consuming and error prone, and the majority of the time will be spent in debugging the test scenario rather than design. Without a good verification randomization infrastructure, it's really impossible to create scenarios where we can test performance and throughput with maximum utilization and with maximum user application in the RE grid. For example, it would be a daunting task to manually come up with a valid allocation of 64 users into a slot within channel types of PUCCH and PUSCH and SRS all together in the same slot. The Section 4 is a proposed solution. The constraint-random infrastructure translates resource allocation requirements briefly presented in Section 2 into SystemVerilog constraint and build the slot map with the desired channel type. This paper will focus on the uplink UL channel types, and its extension to the downlink DL is straightforward. The task of inserting a large number of channel types into a RE grid can be achieved by breaking down the randomization task into multiple stages. At each stage, additional randomization is performed while respecting the dependency of a prior stage. RE grid is maintained as a static array of enumerative field which is shared all the randomization stage, then enumeration constraint or the channel type of the additional state indicator for the resource block in the RE grid. And the RE grid and the enumeration are shown in the program 1. So the first stage of the randomization deals with the determining cell and link level as parameters are unrelated to UE configuration and define the size of shape of the RE grid, such as numerology and bandwidth part BWP, and subcarrier spacing FFT, fast Fourier transform, size of a number of slots. At this stage, and our intended number of the UE is passed to the randomization engine. A list of test modes we have defined and given in Table 2. For the second stage of the randomization, RRC parameters are generated via constraint randomization as per the RRC protocol specification. This includes both G Node B, 3GPP compliant implementation of 5G NR base station, and the UE specification RRC parameters. So some in the UE specification RRC parameters will influence the resource allocation of channels. Bandwidth part size resource block group is RBG size and push RBG config are a few examples where the description of determining RBG size was given in Table 1, and each corresponding SystemVerilog constraint given to a program 2. All of the UE specific parameters are randomized to second stage for the number of UEs that the user intended to simulate, and the UE parameters randomized to be applicable for all slots. The RRC parameters pertaining to the PUCCH that are randomized as data scrambling sequence, DMRS scrambling sequence, F2 max code rate, and F0, F1 initial CS. This is the Table 2 is the 5G NR the randomization test modes. This is frame 2, system value constraint for determining bandwidth part. Start RV size and push PUSCH RVG config and corresponding RV size and P, and the pop ID, group sequence hopping, and F2 num over PRBS. RSC parameters pertaining to push that randomized as data scrambling, XO push, ULPTRs, blah blah blah, and there are or D3 and 4 and 2, 10 or 11 the parameters here. And the URPTR's time density, ULPTR's frequency density, and frequency hopping enable, frequency hopping offset, and the ULPTR's max NR over put, UL unsigned delay, unsigned long, the PTRS early offset, and also PTRS pre, PTRS scrambling sequence. The ARQ hybrid automatic repeat recast, which is combination of a high rate forward error correction and automatic repeat recast related parameters. RSC parameters. The RSC parameters pertaining to SRS that are randomized as scrambling identity and SRS lambda and sim range. This is the figure 3, the hierarchy of the constraint classes. The POW offset reference. At this stage, we have the slope map setter with randomized but empty RE grid as shown in figure 2A. Based on the randomized value of BWP size and BWP start RP, the region that can be used for allocation can be determined, shown by the not allocated region. BW is the active region when all the channel types shall be allocated. The final stage of the randomization can now be performed with the resource grid being ready and with the availability of the randomized UE-RRC parameters. We can start randomizing and inserting the desired UE channel types into resource grid as per the scenario's need. Randomization complexity is the highest final stage, which is a series of randomization, taking a single channel types of the selected user and randomizing the inserting into the resource grid at one at a time. The various channel type parameters decide the placement of the channel type on the resource grid, and the randomization engine will need to refer to the static slope map each time to constrain the placement of the channel type and ensure there is no overlap or violation of any of the specification requirements. The object-oriented structure of the infrastructure divided the randomization effort into various constraint classes as shown in figure 3. Now, the user can develop scenarios use cases using the SystemVerilog universal verification methodology, as known as UVM, to detail the different needs. An example sequence to achieve this is shown in program 3. This sequence is an example, and the order of the insertion is not restricted in any way. Every time a channel type is inserted, the resources of the resource grid will be blocked. The sequence can be kept as simple as possible, and all the complexity is limited to the channel type classes whose handle can simply be randomized to insert into a resource grid one channel type at a time. So the entire randomization stage is summarized in a flow chart as shown in figure 4. That brings us to the complexity involved in the root classes to see how the specification is mapped to a SystemVerilog constraint. The various channel type parameters configuration are derived out of different regions of the specification and to the one configuration of the channel types depending upon its time frequency domain allocation with the RE grid. The scenario generation infrastructure has been designed to tackle this key region of the intersection. This is done by breaking down the channel types, insertions processed into array grid. The static slot method maintained by the infrastructure as shown earlier in figure 2a is updated every time a channel type is inserted into it, and thereby restricting the next item as remaining the available resources only. If we consider x0 and x1 as the time domain parameters and y0 and y1 as the frequency domain parameters, and the region that then needs to be allocated for a particular UE would be a rectangle denoted by the diagonals formed by x0, y0, and x1, y1 on the resource grid. A SystemVerilog constant for allocation of the PUSCH is shown in problem 4. The PUSCH resource allocation is done as part of the third stage, the randomization, meaning the resource grid has already been set up and initialized, followed by the randomization of RRC parameters and the UE specification parameters, which are ready for the use to perform resource allocation. The time domain constraint extracted from the specification are orthogonal to the frequency domain constraint, and the constraint is added to PUSCH base class. The frequency domain constraint differ between the type 0 and type 1 allocation, and due to the large difference between the two types of the subclasses of PUSCH have been made as seen in figure 3. Prior to the third stage randomization call and the set underscore UCL, username and slotname and ccname, function sets the targeted user, slot, and cc where the channel type is intended to be inserted. The array grid has the resource block that are marked as non-allocated, and these blocks are the ones that will be targeted for insertion. The constraint loops through the selected slot, selected CC, and looks for the not allocated resource blocks and automatically uses any available block randomly to allocate the channel type for the given user. At the end of the randomization, the allocated resources are committed to the channel type in the resource grid by marking the allocated resource block at PUSCH and to the intended UE, making it available for the future channel types insertion. The code snippet uses a temporary array grid, array underscore grid underscore act to map the current allocation, which is then saved back into the static array underscore grid underscore map and the end of the randomization. So the corresponding the RBs in the static variables array underscore grid underscore UE are marked the desired UE number. Upon successful insertion into a slot map, or the randomized parameters of the every channel type are stored in the convenience classes object list, which is used to build on the file at the end of the file or the user sequence. This JSON file is generated at time 0 during the simulation and passed on to a Python-based reference model, which uses the JSON file as the configuration to generate true bit input stimulus. Use the injection at top level of the or at block level and expected data used as a golden reference for all desired nodes in the design. So, section 5 is result. The key achievement in multiple-stage randomization is the ability to break down the constraint and isolation the constraint as much as possible in the respective classes, so reducing the potential constraint conflicting among different channel types. So the constraints were contained in the respective parameters, and the only link among the channels were resource availability in the array grid. The resource availability was constraint utilized, so while randomizing the channel type parameters at a time of each insertion. Table 3 listed the number of the parameters that were randomized for uplink. The various features supported by the randomization and infrastructure are mentioned in Table 4. Table 5 provided analytically perspective of the randomization parameters, row and parameter load. the randomization engine would need to handle without a structural breakup of the over-randomization task. Despite of the complexity, the resulting CR has a very low overhead in the verification time. The table 6 depicts the total test execution time of the randomizing and generating verification scenarios based on the 5G CR infrastructure. As in the table, the verification time overhead of CR was around 1% of the total verification time. This is a figure 4, the flow chart indicating one of the possible ways a sequence can generate a scenario. And the table 4 is the uplink feature covered by the constraint randomization infrastructure. So furthermore, the constraint random infrastructure were used to come up with the over 400 high-level test scenarios that were randomized in every regression during the course of the project. The verification infrastructure was complemented with the elaborate functional coverage target the measure of the quality of the stimulus, and the functional coverage infrastructure came with over 80 cover points preliminary targeted channel types parameters. So the table program 4, the time and frequency domain constraint for PUSCH allocation. Time domain constraint covered the entire PUSCH space and was part of the PUSCH base class, and while the frequency domain and constraint were split into separate classes based on time, constraint for type 1 are shown. Table 5 is a randomization load analysis for a 64 UE insertion of the PUCCH FMT 0 and PUSCH type 1 and SRS into one slot. The multiple test scenarios could be created during the CR infrastructure and combined with the random seed. The verification goal was effectively achieved to random constraint-random scenarios derived from Wall 428, and after having run multiple seeds every week, and over 80 RTL-based post-design freeze were caught. Most of the bugs that were caught were critical, resulting in a hang or bite in a specific scenarios. The CR infrastructure was instrumental in generating thousands of random scenarios in combining all the channel type of the multiple UEs within a slow, exercising and stressing the design in the way that directed test wouldn't do the justice. Multiple performance sequences were added, such as maximum throughput, the full allocation, max CC, and the stress sequence, with a 64 UE allocation over multiple slots and PUCCH from a too large RV allocation with high payload sizes. The CR infrastructure was easily used at various levels of the test bench. A simple plug and play, and one of the most used features was to reply a failing test without the need to randomize. Most importantly, we could take a test failing at one level, unit and display and it's another level, type of the vice versa, and this was useful to replay many top level failures at the respective block for the faster turnaround. The next is the section 6 conclusion. In this paper, we have successfully created a constraint for a full 5G uplink. Constraint were hierarchically divided into multiple stages and utilized the common array grid to tie all channels together. This resulting constraints were easy to manage, and the sequence could be written to a direct verification toward less covered configuration. Overall overhead of generating a valid sequence 5G uplink scenario was approximately 1% of the total verification execution time. So this shows that even with a system as complex as 5G NR with a hierarchical multi-stage approach in writing constraint, system-level CRV is possible with a low overhead. So this is the DVCON US 2090, and this is the US DVCON is US 2020, and this is the DVCON Europe 2014. The reference one is system-level random verification, how it should be done. SystemVerilog constraint operation you are forgot in school to get better result. What you forgot in school to get a better result. and the top most common SystemVerilog constraint-random gotchas. Okay. The others are about the NR, 3GPP, and documentation. Okay, today, thank you for your time, and see you next time. Today I read this paper, Constraining 5G testing scenarios in constraint random way. So again, thank you for your time, and see you next time.